So let's talk about compound interest. So the interest is added to the principal regularly so that the added interest may also increase. It's just that the intervals that it's added are more frequent. So as a reminder, simple interest, which we talked about on Wednesday, compounds interest once per year, whereas we can compound semi-annually, which is twice per year, quarterly, which is 4 times per year, monthly, which is 12 times per year, weekly, 52 times a year, daily, 365 times per year, or you could, there's even, right, there's all kinds of sorts of different intervals. You could do it minutely, once every minute, which would be 525,600 times per year, and larger and larger numbers. So let's talk about the formula. The formula is going to be essentially the same as it was yesterday with one small addition. So here's our compound interest formula. Hopefully you guys can, let me change one video setting here so that maybe you can see my board a little bit more easily. Yeah, let's change that. Cool. Let's actually, hopefully that's a little bit easier to see what's written on the board there, but I will still say the words even if you can see it. So this says A of t equals P times 1 plus R over N to the N times T power, where A of t is the amount of money you have at time T, P is the principal or starting amount, R is the interest rate written as a decimal, right? So it's 15%, it's 0.15. If it's 2%, it's 0.02. N, this is the new thing, is the number of times we are going to compound interest every year. And lastly, T is the number of years we are compounding the interest for, or calculating interest for. So it's probably worthwhile to memorize this formula. I mean, obviously you'll be able to look it up if you ever need to access it, but it's nice to not have to look things up every time you want to know what they are. So I would definitely recommend memorizing it because it comes up somewhat frequently. Whoops. So let's see here. So let's look at some examples. And feel free to ask questions or let me know if you have questions or if you have other things. So it's always a struggle to get the right lighting here. So let's look at this first example. We have $1,000 to invest. Our plan is to invest it for 10 years. So we're going to invest this money for 10 years. And our choices are in an account that earns either choice 1, 6% simple interest, or choice 2, 6% interest compounded quarterly. Quarterly or monthly, sorry, compounded monthly. And so what we're going to do is we're going to put these two different situations into our formula and see what's better, right? We want to know what's the better choice. And there's going to be a hopefully not too surprising answer here, but the point of this is really to see the effect of compounding. So for this one, the amount of money after 10 years. Well, actually, let's write down what things are first. So time is 10. Our principal is $1,000. Our interest rate is 6%, which is 0.06. And for this first one, right, for this situation here, for simple interest, the number of times we're compounding, it's going to be 1 time per year. For compounding monthly, we know we're going to compound it 12 times per year. Let's see what happens. So for the simple interest, we're going to get the amount of money after 10 years is going to be the principal, $1,000, times 1 plus r, which is 0.06, divided by 1 to the n, which is 1 times t, which is 10 power. Simplifying this a little bit before I put it into a calculator, this would be $1,000. 1 plus 0.06 over 1 is just 1.06 to the 10th power. I certainly can't calculate 1.06 to the 10th power on my own, so I use a calculator and I get approximately 1,000 times 1.79085, which becomes $1,790.85. And again, I'm just putting in 1.06 and raising it to the 10th power and multiplying it by 1,000. Okay. So again, that's where we said basically every year we're going to take 6% interest. So after 1 year, you're going to have $1,000 plus 6%, which is 60. And then after another year, you're going to have your $1,060 plus 6% of that, which would be $60, $63.60, and so on and so forth. So each year you're getting a little bit more. Here, on the other hand, you're compounding your interest monthly. So what we're going to do, we're going to say that for this one, the amount of money we're going to have after 10 years. Same formula, except now the n is going to be 12. So it's going to be still my principal, $1,000, times 1 plus my interest rate, 0.06 divided by 12 to the 12 times 10 power. And again, I'm going to simplify just a little bit before I actually write this out. So this is 1,000 times 0.06 divided by 12 is 0.005. So this is going to be 1 plus 0.005, which is 1.005, to the 12 times 10, which is 120th power. And here's what I want you to kind of see about this. In this equation, I'm essentially compounding 6% interest 10 times. In this equation, I'm compounding 0.5%, right? 0.005 is half of 1%. I'm compounding 0.5% 120 times. So in 10 years, there are 120 months, and every month I'm getting 0.5% of interest. So 0.5% after 1 month, another 0.5% to be 1%, another 0.5% to be 1.5, another 0.5% to be 2, all the way up to through the first year, each of those 12 0.5% will end up being 6% of interest for the first year. But it's going to add up to a little bit more because every time I give myself 0.5% of interest worth of income, the next 0.5% is going to be 0.5% of the new amount of money I have. So, right, so for this example, right, like 0.5% of $1,000, well, 1% of $1,000 is $10. Half of that is $5. So after 1 month, I've got an interest that's $5. And then after the next month, I'm going to get another 0.5%, but it's going to be a little bit more than $5 because it's going to be 0.5% of $1,000 and 0.5% of $5. So you can see, I think, right, I'm going to get more than $60 that way that first year. So I'm going to get $5 the first month, a little more than 5 the second, a little more than 5 the third, all the way up to the 12th month. I know that 5 times 12 is 60, so a little more than 5 times 12 is going to be a little bit more than 60. Whereas in this one, the first year, I definitely only would have gotten $60. Using a calculator, this ends up being, after 10 years, approximately $1,819.40. So, I mean, not a huge difference in 10 years, right? It's about, what, 10, 20, almost a $30 difference in 10 years. Not super, like, a lot of money, like, wow, it's really better to compound it monthly, but also it is better, right? It's not insignificant. So what we're going to see, or what we do see here, is that if everything else is the same, the more frequently you compound interest, the more of a return you get at the end. That's always true. Greater number of times compounding means more dollars at the end of the process. So let's look at another question. So let's say, suppose we invested, so I'm just going to write down the pertinent information. So you can look at the question in the notes if you want. I'm going to write down what we need to know. So suppose you invested $5,000. So our principal is $5,000. into an account that pays 4% interest. So our interest rate is 0.04, right? That's the same as 4%. Compounded weekly. So compounded weekly, not W-E-A-K, right? It's not week, it is week. And that's a terrible not pun, really. Compounded weekly means N equals how much? How many times are we compounding per year? Well, I would say 52. Technically, there are 52 weeks and 1 day in a year, unless it's a leap year and it's 52 weeks and 2 days. But we typically just say 52 weeks. We don't say like 52 and 1/7. That would be silly. What else do we have? And then we have the question. How long? So when you see the words how long in the beginning of the question, you should automatically be thinking, okay, I'm trying to solve for time, right? If they're asking me how long it takes, T is the variable I'm trying to figure out. So how long until we've doubled our money? All right, so let's set up the equation. And again, I like to write it down just in case I've forgotten it. It's A of T equals P times 1 plus R over N to the NT power. So I'm just going to throw in everything into my equation. So my principal is $5,000. I don't need to write the dollars in every time you do that, but you can. R is 0.04. N is 52. N is 52. And we know we're going to be solving for T, so I'm just going to write T. And now, what should the amount over here be? If I'm trying to double my money, and I'm starting with a principal of 5,000, this should be how much?
10,000.
Yeah. And then we're going to solve for T. We're going to start by dividing by both sides by 5,000. Right? So I'm trying to isolate the variable T. So 10,000 divided by 5,000, not surprisingly, is 2. And that usually happens, right? If the question was going to be how long does it take to triple your money, after you did the first step, you would get a 3 there. Or if you're talking about half-life and you're trying to find out how long a half-life of something is, after you did the first step, you'd have a 1/2 over here. It's kind of always a true thing. And then what? That's a good question. So what do we do next? Well, I have a variable in my exponent, and the way we usually get variables out of the exponent is by taking the logarithm of both sides. And you can either use log base 10, you can use the natural log, you can use log base 2. Log base 2 feels weird, even though log base 2 is nice. I would probably use log base 10 here just because, I don't know. For things like this that are dollars and cents, for some reason log base 10 seems like the more appropriate base. Either log would be fine. So I would say log base 10 of 2 equals log base 10 of all this stuff. 1 plus 0.04 over 52 to the 52t. And the whole reason we do that, so that then this 52t, right, this exponent can come down in front. So we can write this as log of 2 equal to 52t times log of this, right? And this is 1 plus 0.0452 is approximately 1.00077. This bracket looks like it's kind of in the way there. Okay. So then I'm just going to solve for t. So I'm going to divide both sides by 52, and I'm going to divide both sides by log of 1.00077. So t is equal to log of 2 over 52 times log of 1.00077. And if someone said they wanted an exact answer, or you would leave it like this. Actually, you'd probably leave it as log of 2 over 52 times log of 1 plus 0.04 over 52, because that's a little more precise. But the question here, right, this answer, although is correct, it doesn't really tell me what I want to know, right? Like I asked how long it takes to double the money, and if you tell me that the amount of time it takes is log of 2 over 52 log of 1 point that, right? That doesn't tell me how long it takes. So here it is definitely appropriate to find the decimal approximation. And so we throw that in the calculator and we get about 17.32 years. So that's what I would say. It's about 17.32 years, or 17 years and almost 4 months. So yeah, interesting. So now I want to talk about a very specific example. As usual, you're certainly welcome to take notes or not. Like, the notes are all on Canvas. But this specific example, I usually tell my students you don't have to take notes for this, because the idea really isn't to write down the stuff. It's to kind of understand what's happening. But really, I certainly would always take notes because I find it useful to remember later what was happening. So here's the setup. I, being a nice guy, I'm going to loan you one whole dollar. I know, it's not a lot of money, but it's still nice. I'm not that nice though. I'm going to charge 100% interest. It's kind of steep. I'm a loan shark. For a period of 1 year. The question I want to ask is, depending on how frequently we compound the interest, how much will you owe me at the end of the year? So that's the setup. Let's write the equation. So once again, we have the usual equation, the amount of money at time t. Well, t is 1 year. Let's write that is p times 1 plus r over n to the nt. Plugging in all the things we know, the amount of money after 1 year. So I could write a of 1. I could just also write a. The principal is $1. N, the number of times we compound things, is going to actually vary, right? N is going to be as little as 1, as big as we want it to be. Oops, sorry, the N, that should be an N. And then what's the interest rate? It's 100%, but how do I write 100% as a decimal?
1.
Just 1, yeah. So here's my equation. The amount of money I'm going to have after 1 year is going to be 1 plus 1 over n to the n. And I really want to make a chart to kind of show what we get. So I'm going to go to the other side of the board here, because I'm not going to have enough room to really write down everything here. So that's how many dollars you're going to owe me at the end of the year. It's 1 plus 1 over n to the nth power dollars, depending on how many times we compound interest. So I'm going to make a little table here where n is the number of times, and the a, which is the amount you're going to owe me, is 1 plus 1 over n to the n. Now let's just start with simple interest. Let's say we only compound interest at the end of the year. So if n equals 1, the amount of money you're going to owe me is going to be 1 plus 1 over 1 to the 1. 1 plus 1 is 2. 2 to the first is $2. Which makes sense, right? If I loan you $1 and I charge you 100% interest at the end of the year, you owe me the $1 back plus 100% of interest, which is another $1, which is $2. Okay. So now, what if I charge you interest semi-annually, so twice a year? So that's going to be 1 plus 1 over 2 squared. And I really want to talk about this because this is the example I feel like is usually most digestible for people to really get what's happening. I'm charging you half of the interest twice per year, once after 6 months and then once after 12 months. So here's what's happening. in the first 6 months, right? So after 6 months, I'm going to earn 50% of the interest, which is 50%, right? So you're going to owe me the dollar plus 50 cents, right? So it's right at the beginning, I've lent you $1, so you owe me $1. And then after 6 months, I'm going to earn half the interest. So you're going to owe me $1.50. And then after another 6 months, you're going to owe me the other 50% of the interest, but it's not 50% on the dollar, it's being compounded. So you owe me 50% of interest on the $1.50, which is 75 cents. So you're going to owe me really $1.50 plus 75 cents, which is $2.25. Right here, it was $1 plus 50% of that $1, which is 50 cents. Here, it's the $1.50 you now have, or I have, I guess, plus 50% of that. And that's exactly what you get by doing this calculation, right? 1 plus 1/2 squared, that's equal to, so I like fractions. This is 2 halves plus 1/2, which is 3 halves. 3 halves squared is just 3 halves times 3 halves, which is 9/4. And 9/4 as a fraction, or sorry, as a decimal, is exactly 2 1/4, or 2.25. So yes, it totally works. So we can see that if I charge you interest, and we know you do this, right? If I compound the interest you owe me more frequently, I'm going to get more money. So what if I do it quarterly, 4 times per year? Well, then I'm going to get 1 plus 1/4 to the 4th power, which is where I start using a calculator because things get messy. So that's 1.25 to the 4th, which is approximately $2.44. If I compound the interest monthly, so 12 times, that's going to be 1 plus 1/12 to the 12th, which is approximately $2.61. So here's a good question. Can I triple my money? If I compound interest enough times per year, can you end up owing me $3 at the end of the year? Let's find out. So if I do it 52 times per year, right, weekly, 1 plus 1/52 to the 52nd power is approximately $2.69. If I do it daily, so 365 times per year, I get 1 plus 1/365 to the 365th power, which is approximately 2.7145. I'm writing out a lot of decimals here because I want to point something out. 67482. You can also do it minutely, right? Every minute. I'm not going to do that here. It'd be 1 plus 1/525,600 to the 525,600 power. But here's what's happening, right? We seem to be getting kind of stuck. Right? We increase, from here to here, we increase by 17 cents, from here to here, 8 cents, from here to here, a little more than 2 cents. It seems like we're getting close to what's called a limit, right? Some kind of boundary that we can't get past. And there is a boundary. So if you compound the money continuously or an infinite number of times, the amount of money you're going to owe me gets closer and closer and closer to the number E, which is approximately 2.7, but it is more specifically approximately 2.71828 459045. That is the only number I know to any significant number of decimal places. But that's how much money you owe me. So if I compounded interest continuously or compounded an infinite number of times in that year, you would owe me $2.72, not triple. So the real point of this exercise is to learn that if you take the limit of this expression, right, as you let n get infinitely large, like I want to say this again, so as n goes to infinity, that's what that arrow means. As n gets infinitely large, this specific expression, 1 plus 1 over n to the nth power, this gets closer and closer to e. Ooh, in fact, we could even graph it. Let's do a graph real quick, just to kind of. That's an excellent idea. I'm so happy I thought of that. So let me share my screen. Here are the notes. Let me pull up Desmos. Okay, I want. The nice thing about Desmos is you can usually use whatever variables you like, which is kind of nice. So there's the thing, 1 plus 1 over n to the n. And we can see, right, if we plug in 2, we get exactly 2.25. If we plug in 4 for n, we get 2.441. And then if we zoom out a bit, I remember how to zoom out. Yeah, there it is. Right, we see, yeah, that's looking like it's getting really close to 1 value. If I zoom back in a tiny bit, if I also graph the line y equals e, which is about 2.7182818, right? Look, right, that the graph in red is getting super duper close to the graph in blue, but it's never actually going to get there, right? You could go out as far as you want, and it's getting closer and closer and closer. And if you keep zooming in, right, you can see, oh yeah, they're not, the red one's always going to be below the blue one. So it's getting closer and closer and closer and closer, and where you could go on forever to that value of e, but it's never actually going to get there. So the right, and you could go way out. Right, you go super big, boom, you go back in. I know it's kind of dizzying, right? You're like, what's he doing? And if we go back into this really big number, right, they're super close to, like, they look like they're overlapped. But eventually, if you get close enough, you will see, oh yeah, the red one is still below. That's kind of a neat thing to do. It's nice to graphically see what's happening with a lot of these things. So that is the whole idea. So let me stop sharing here. This limit, the limit as n goes to infinity of 1 plus 1 over n to the n equal to e, is a very important limit. It is one that comes up a lot in calculus. So that is why we are spending time talking about it, because it definitely, you will see it again for sure. So if you remember anything from today, even though the compound interest formula is important, this is probably the most important thing I've said today for your future in math. You want to remember this. This thing, 1 plus 1 over n to the nth power, as n gets larger and larger and larger, this thing gets closer and closer to e, which is about 2.7. Okay. And the idea, well, actually, let me check one thing here. Another reason we like to talk about that, though, is because this then means that we can continuously compound interest, and there's a different formula for that. So, right, in fact, this is kind of, yeah. So this expression, so, right, if we compound n times per year, this is what we get, right? The amount of money after t years is the principal times 1 plus 1, r over n to the nt power. But if we let n go to infinity, so if n gets infinitely large, we're no longer compounding n times per year. I mean, we're compounding an infinite number of times per year, but we usually use the words that we are compounding continuously. And what happens is, as n goes to infinity, this expression gets rewritten as p times e to the rt power, or pert, as a lot of people like to say. That's what I definitely say. I think they still make shampoo, right? 2-in-1 conditioner. The reason for this is because of what we just said, actually. You guys don't need to know how to get from here to here, but the idea is that you can rewrite this as 1 plus r over n to the n over r to the tth power. And then, let me actually do one thing here, sorry. This is equal to That's not quite right. There's an R that I'm missing up here. So if you guys look at this and this, they're actually not the same, right? I divided that by R and I didn't multiply by R to fix it. So there should be an R there. And then this part is going to E because you have 1 plus a thing to the reciprocal of that thing. And so then you're getting P E to the RT. So that's what's happening there. If you have more questions about this, I would say one, you don't really need to sweat how this goes to that. But if you want to talk more about it, I'm free during office hours or after class today. If you're like, how does this really work, James? I can definitely say more about it, but it's not like the focus of what you should be thinking about. So don't worry about this. But if you want to worry about it, come talk to me later after class or during office hours another day. So let's do some examples. So the thing you want to remember is that's the continuous formula. That's the, I should really write, this is A of t. That's the compounded some finite number of times per year formula. And really, both formulas will be there in the notes available to look at. Just also remind everyone there is a quiz that will be available after class today until tomorrow. It's got a few questions on it. I think I gave you guys an hour to do it because that should be more than enough time. So once you start it, you'll have an hour. And then after you finish it, please do upload your answers that you've written down. And I want to see the work. So please show me as much work as you think is necessary, or even more if you think you might not be showing enough. So let's look at this next question. Suppose you invested $100. So our principal is $100 into a savings account that compounds continuously. So we're compounding continuously for 20 years. And then at the end of that 20 years, we have $500. What was the interest rate? So most of these questions, like I was kind of saying on Wednesday, they're going to give you essentially all the information you need except for the one thing you're trying to solve for. So we should have everything we need except for the interest rate, and we're going to solve the interest rate. So here's our formula. The amount of money after time t is P e to the RT. And I'm just going to put everything into this formula that I know. I know that the principal is $100. I know that the interest rate is what I'm trying to solve for. I know that t is 20. I know the amount of money after 20 years is $500. And we can solve this. So whenever you're trying to solve something where you've got the variable and the exponent, before you can take a log of both sides, you have to get rid of any coefficient of the thing that's raised to a power, whether it's e or 10 or 2 or whatever. So you have to get rid of that coefficient by division. So I'm going to divide both sides by 100. So 500 divided by 100 is 5 equal to e to the, I would probably write this as 20 times r. But r times 20 is also fine. And then I'm going to take the natural log of both sides. The natural log of 5 equals the natural log of e to the 20r. And you can either bring down the 20r and then say 20r times natural log of e, but natural log of e is 1, right? Because again, this is log base e. Log base e of e to the thing is just the thing. If you don't like that, you can also go this way and say natural log of 5 equals 20r times natural log of e. But natural log of e is just 1 because you're asking e to what power equals e, and e to the first power equals e. Okay. So then either way we're solving this equation. So divide both sides by 20 to get that natural log of 5 divided by 20 is equal to your interest rate. Now, that's not a very nice answer, so then we should actually use a calculator and say, okay, if you do that, you get that R is approximately 0.08. So I would say that the interest rate is approximately 8%. Okay. A couple more examples here. Example. Our goal is to have $2,000 in 4 years. The rate of interest is 10%. That seems like a lie. And we're compounding monthly. How much do we need to invest? So what am I really asking for? In my equation, A of t equal to P times 1 plus R over N to the NT power. What's the thing we're trying to find if we're asking how much we need to invest?
The principal?
Exactly. So that, which also means we should probably be able to fill in every other thing, right? So the amount we're trying to get is $2,000. The principal that we're going to try and solve for. The interest rate is 10%, or as a decimal, 0.10, or just 0.1. The number of times we're compounding is 12. And the number of years we're compounding for is 4 years. So here's what we're trying to solve. 2,000 equal to P times 1 plus 0.1 over 12 to the 48th power. And all you can really do is divide by this to solve for P. So P is going to equal 2,000 divided by 1 plus 0.1 over 12 to the 48th power. And the way I would do that with my calculator is I would first do the bottom. So I would say, okay, so 1 plus 0.1 divided by 12. That's going to be about 1.00833333 forever. Then I'm going to raise that to the 48th power. That's going to give me about 1.489. And then I'm going to do 2,000 divided by that answer. And I'm going to get $1,342.86. So that's how much money we have to invest, so that after 4 years, if our money is earning 10% interest compounded monthly, we would end up with $2,000. Exactly. Okay. So a different question. The last question. Might even have time to answer other questions. But there was something I wanted to say. Something kind of not cost related. Hope you guys are doing all right in general. So I should also say we have a test coming up next Friday or next weekend. So Monday class we'll do class I, which I don't remember what it is off the top of my head right now. And then on Wednesday we'll review, and then on Friday, I think what I have scheduled for Friday is more review. Let me actually double check now that I'm thinking about it. Let me look real quick here. All right, one moment. I just want to see, just to be sure. So yeah, so next Wednesday is midterm one review / maybe catch up if we're behind. I don't think we'll be behind. And then Friday is just the midterm scheduled. So obviously I'm not going to have the midterm that you take during class. It'll be kind of like the quiz and it'll be available after class. But it'll be available for, like, you'll have a longer period of time. And it's not going to be something that you submit in grade. Well, it's not going to be like the quizzes where you just write your answers in Gradescope. It's going to be more like a homework assignment where you're going to have the exam available to you and you're going to write down your answers and upload your PDFs. So it won't be entering stuff in Gradescope like you have been doing for quizzes, just in case you were curious about that. It's to be kind of like, I mean, it's essentially like a take-home exam. You take it home, you do it, you turn it back in. We can talk more about it on Wednesday though. So let's finish this last example. We're running out of time here. We have $1,000. So our principal is $1,000. And we want to grow it to $2,000 in 4 years. So we want the amount of money after 4 years to be $2,000. We're compounding continuously. And the question being asked is, what interest rate do you need if interest is compounding continuously? So what is the interest rate we are looking for? So continuously means we're looking at this setup. The amount of money at time t is P times e to the RT. And again, just like the previous ones, we're just throwing everything into the formula and then solving for the thing we're asked to solve for. So the amount of money is going to be $2,000. The principal is $1,000. E is just the number E, right? You should be using the number E, not that it's approximately 2.7, but actually the number E. And then the interest rate that we're trying to solve for, and T is 4. We know how to deal with this, right? We've solved these kinds of equations already. So divide both sides by 1,000. 2,000 divided by 1,000 equals e to the 4 times r. 2,000 divided by 1,000 is 2. So 2 equals e to the 4r. Take the natural log of those sides. Natural log of 2 equals natural log of e to the 4r. And then this, so I'm just going to say this because it comes up a lot. The natural log of e to a thing is just the thing. So the natural log of e to the 4r is just 4r. So 4r equals the natural log of 2. And then solve for r by dividing both sides by 4. So the natural log of 2 divided by 4 is equal to r. That would be your exact answer. And then if you use a calculator to approximate that, I'm going to get the natural log of 2, which is about 0.69, divided by 4 is about 0.173. So r is about 0.173, or written the way we probably should write it if we're answering a question, r is about 17.3%, which is a pretty high interest rate, right? You have to have a high interest rate to double your money in 4 years.